afternoon, everybody. So I'm going to talk a little bit about the power electronic hardware itself, and I'm going to start off by just talking about how the soft open point converter actually works and what it actually does. So I'm going to use this example. This is our two-terminal street furniture device. We put it into a normally open point location, and by putting it into that location, we effectively mesh two different parts of the network that are fed by, in this example, substation A and substation B. It allows us to transfer power between substation A to substation B and vice versa. Now, not only can we transfer power between the two substation feeds, but we can also transfer power between the phases of each line. So that's something that we built into the architecture of the system to allow us to do that. Normal three-phase inverters tend to just balance on three-phase, but we can do it per phase. Now, being power electronics, we have control over both active and reactive power. So, having control over reactive power, we've meshed it 2 points of the network, so we can control those nodes to control voltage. So we can do voltage correction. If you've got reactive power and active power control, you can do power factor correction. It's a fast device, but all power electronics is very fast, so we can actually cancel the harmonics in the network as well. So what does that all actually mean? That's all great, that's lovely functionality. What it actually means is we can transfer power from an overloaded place to a not so overloaded place, and if we can reduce losses, then we can get more out of the existing assets. We defer reinforcement, and we help the uptake of electric vehicles and distributed generation. Quite a simple kind of model in that sense. Where we started and where we're going. So Alex mentioned FunLV. FunLV was a project we did 4 or 5 years ago. This particular converter on the left here, this was the two-terminal converter that we put in the street, at 240 kVA in rating. You can see it's got three-sided access. It's a little spinning model. And it was great. It proved that, and the 3T proved that the soft open point principle fundamentally works. You can transfer power, you can do all of those things I've talked about in the previous slide. What became apparent was there was a few things we need to do to this to make this more practical and a bit more commercial solution that could be considered in the network. So hence active response picks the project up from this point. And what you can see here is the first generation of, the second generation of the SOP that we're developing for active response. The key difference here is the device on the right for active response switches a lot quicker than the device on the left. Now that solves a couple of issues. First of all, if you switch at 5 kHz like we did on FunLV, you can hear it, you get a whine. If you switch at 20 kHz like we're doing on the system on the right, it becomes inaudible to us anyway. We may have a few dogs howling in the area, but human beings should be okay. So we can switch faster, so it's a lot more quiet. We've got two things we want to address with the architecture itself. First of all, this particular device on the right-hand side is a lot more efficient. Now, if I point at these devices here, these are the reactors. If I switch at 5 kHz, those reactors are very big and they produce a lot of heat. These are the reactors on active response. They're a lot smaller, so we generate a lot less heat, lower losses. Now, in this system, we were generating about 12 kilowatts of heat. That's a lot of heat. We need a lot of air to shift that amount of heat. So moving to this particular system, we reduce the losses to something more like 5 kilowatts. We don't need to move so much air. The system becomes a lot quieter. So we near eliminate the forced cooling. The next thing, what's really important we found with the trials is practicability in terms of service and how much of the pavement you actually use. So this system having three-sided access, that's quite a large operational footprint. This system has got a completely different form factor, and that enables us to create a much slimmer model, and we can put it against the edge of the pavement, not roadside, the other side, and that gives us single-sided access and uses way less of the pavement up. So it's more space efficient. How are we doing that? Well, we've got this wonderful technology called silicon carbide semiconductor technology coming through. It switches faster, it has lower conduction losses. It's quite hard to get hold of, we have found. That's the downside of it, but we're overcoming that challenge. So that's great. That's LV for you. Now, Alex introduced us to doing this at 11 kV. Now, so the question came to TPS, how are we going to take a soft open point converter, which is back-to-back architecture, and deploy it in the 11 kV network? There are a couple of challenges in doing that, which I'm going to sort of talk through here. So we want to mesh at 11 kV. And what we really want to do is to keep the functionality of the soft open point that I talked about. Well, we managed to do that minus a complete operating envelope around phase angle and voltage limitation. I'll come back and talk about that. But the reason we made that trade-off is there's a significant challenge of taking a back-to-back converter to MV. It becomes very bulky. We have to use a modular multi-level design, and it becomes very expensive. So it starts to become not commercially viable. So we looked at this as we need something else. We need to come up with a different architecture. So we transferred the learning of, well, silicon carbide can do something for us. It will reduce the losses, make things smaller, etc., etc. But we need something else. So we came up with a novel architecture that allows us to use a part-rated converter to do effectively a 5 MVA link. So it's only a 1 MVA rated piece of electronics. So you're probably thinking right now, that's a unified power flow controller, right? Actually, yes, it is. It's fundamentally a unified power flow controller. Difference being, we've put a different architecture. We've come across a different architecture for this device, so it is quite novel in many ways. So I talked about that phase and voltage angle limitation. So I'm going to talk a little bit more about that. So first of all, here is effectively the same at the 11 kV level that we had for the soft open point. We can see here we've got two networks, network A, network B, and we're meshing with the device in the middle. That device comprises the power electronic converter, an auxiliary transformer, but you can see it's in parallel with the network. Because we're very sensitive at 11 kV to protection, we need to protect the device, we have a series switch which is actually a solid state device. So again, this is semiconductor technology. Now the way this system works, it works on controlling voltage vector. Voltage vector in both magnitude and phase, unlike the soft open point, which is a full power transfer system. So that has its limitations, and I'll just quickly talk through these. So we have here a limit to the equipment. So this is a voltage limit that's applied to the equipment. Now if we put this equipment between the networks and the voltages are balanced, then where this blue line crosses this limit, that's our phase angle limit, which is approximately 10 degrees. As this becomes imbalanced, we've got a line here where we have a 6% voltage difference and we cross our limit at about 9 degrees. We go even further still, we get to a 12% delta and we cross at about 7 degrees. So where we set the specification, which was phase angle of 8 degrees, we're going to come in roughly at around about 9% voltage handling capability, or the difference between the feeders. So you ask, is that good enough? Is that realistic? So we did some trials, we did some data monitoring on the trial site, so we found that phase angles we typically saw well within those limits. So it remains to be seen as we do the trials whether we stay in those limits, but things look pretty good. So on that, I'll pass you back to Alex.